In this lesson, you will learn to recognize and analyze normal distributions. Now the question is, what is a normal distribution? Well, let's say we were to collect some data on the number of students who received a certain grade in a class. So let's say we collect the data and then we draw a histogram with the data. So here's our histogram, where on the x-axis we have our scores. So from here to there is going to be your F students, and then from this point to this point we have our D students, and then from there to this point we have our C students, and then B students and A students. And the y-axis is the number of students who receive that score. So let's say within a certain class we have, let's say, 5 students who receive an F. So here are 5 students. And then for the D students, let's say we have maybe a few more students. So we have like 8 students, for example. And then the C students will have a few more, and let's say maybe 13. So we have 13 students who receive a C. And then the B students would be fewer, probably. And so we'll say we have 10 B students. And so that's 10. And then the A students would be not as many as the B students. So let's say we have 7 A students. So notice with this graph, if we were to connect the corners, so starting from here, connect to this corner, and then up to the C's, and then down here like that, connect this corner and this corner, and we are going to get a graph that looks something like this. Notice the effect is kind of along these lines right here. And anytime we collect data where the data would create a graph like this, we call that a normal distribution. So many different things in everyday life would be considered a normal distribution, such as heights, for example. If you're referring to the grades of a student, if you're referring to maybe the average pay of a person, and you were to graph out the pay of every individual, you would get something along these lines, where the majority of the people or the data would fall within the certain range here in the center, which would be like the average, the mean. And then you have a few people who are the outliers, as we call them, that are maybe more wealthy or get better grades than other people. Then you have a few people on the other end that receive worse grades or have lower pay than everyone else. So this would be considered a normal distribution. Now we have another specific kind of normal distribution called a standard normal distribution. And we have a picture over here on the side, where with the standard normal distribution, by definition, the mean or the average is 0, and the standard deviation of the data is equal to 1. Now obviously, in most scenarios in everyday life, the average will not be 0. Right? The average height would not be 0, the average shoe size, the average pay would not equal 0. And the standard deviation would not typically equal 1. But with the standard normal distribution, by definition, the mean is 0 and the standard deviation is 1. With a standard normal distribution, it is symmetric with respect to the y-axis. So if you were to draw a line down the center, right here, then it is symmetric about this line, where the left side is identical to the right side. In addition, it is what we call asymptotic to the x-axis, meaning that you see this curve right here is approaching the x-axis, and on the other side as well is coming down towards the x-axis. Well, in reality, it is asymptotic to the x-axis, meaning it will get infinitely close but never actually reach the x-axis. Also, the area under the curve and above the x-axis is equal to 1. So if I were to find the area of everything inside of this curve, so everything here inside, then that area would equal 1. Now, one reason why it is important to know these things about the standard normal distribution is because we will have a table that we can use to analyze the data with a standard normal distribution. Now you might be asking, well, why do we need to know how to use a table with a standard normal when most scenarios in life would not be a standard normal distribution? Well, the reason is because at the end of this lesson, we'll show you how to convert into a standard normal so that we can analyze the data using the table. So here's a table that you need to know how to use. With this table, we see that we have two columns. We have an X column and then the area column. And you see that the columns are repeated, so we have 3 sets of X and 3 sets of area. So how to interpret this table is we look at an X value. So let's pick 0.8, for example. So looking here at 0.8, there's an associated area with it. What the area means is that if you were to find the area between 0.8 on the x-axis, so 0.8 is right here, approximately, the area between 0.8 and 0, so between 0.8 and 0, would be 0.2881. So this area is 0.2881. And that is how to read the table. So for any of these, say we picked 1.8, the area between 1.8 and 0, so 1.8 and 0, all of this, would be 0.4641. And keep in mind that the standard normal curve is symmetric, meaning the left side is identical to the right side. So for any of these x values, let's say we did negative 0.8. So here at negative 0.8, we want to find the area between negative 0.8 and 0. So over here, well, to find that area, it's the same area as it is on the right side because it's symmetric. So the area is still 0.2881. And if you know how to interpret this table, you can answer any question that we could ask concerning the curve. So I'm going to walk you through several examples of all the variations of the types of questions that could be asked. And then after that, we'll get into how to convert into the standard normal so that we can analyze the data for any distribution. So here we see we're asked how much of the data is between 0 and 1.0. So only part of the table is given to us, only the part that is relevant. And so between 0 and 1.0, we're trying to find this area right here. So this area, based off the table, we'll need to look at 1.0 and then the corresponding area right there. Well, the corresponding area, the 0.3413, by definition of the table, tells us that this area is 0.3413, the area between 1 and 0. So this one is very straightforward. The table tells us that the area between 1 and 0 is 0.3413. And so that's the amount of area in between. And if you want to convert that to a percent, you would have that written as 34.13%. Another question that could be asked is how much of the data is greater than 0.4. So 0.4 is approximately right here. And how much of the data is greater than that? So we want the area from here and then everything off to the right. Well, we don't know the area yet based off the table, because if we look at 0.4, the area 0.1554 finds me the area between 0.4 and 0, which would be right in there. So we know that to be 0.1554, but the question is not asking the area in between 0.4 and 0, but how much of the area is greater than 0. So going back to our definition of the curve, the area under the curve is going to equal 1. So the area is equal to 1. And that means half of the curve is going to equal 1/2, or 0.5. So over here, everything from 0 on, this way, all of this area is going to equal 0.5, because that is half of the graph. So if I simply take 0.5 and subtract this 0.1554, I will find the area over here, which is going to be 0.3446, which can be converted to a percent as 34.46. And we know this is going to be true because if we add 0.1554 plus 0.3446, we're going to get 0.5, or half of the area of the graph. Here we're trying to find the area between 1.4 and 1.8. So something like this, between 1.4 and 1.8. Well, this one, we're looking at two different corresponding areas, right here and then right here. Now remember, this area given to us is the area between the x value and 0. So if I were to look at this, between 1.4 and 0, this area is going to be 0.4192. And the area from 1.8 to 0 is going to be 0.4641. And the area 0.4641 will include this area that we're trying to find, but it also includes everything over here that we already found. We already know is 0.4192. So we have an overlap there by 0.4192. That is going to be true for both areas. So to get rid of that overlap, what I do is I simply subtract the 0.4641 by 0.4192, which will give me 0.0049, and convert that to a percent, we have 0.49%. And sorry, this should be 0.0449. So that's going to be 4.49%. Next example, we're asked how much of the data is less than 0.4. So looking here at 0.4, it's approximately there. How much of the data is less than 0.4? So looking at the table, the area that corresponds is 0.1554, which is the area between 0 and 0.4. So this area in between is going to be 0.1554. But the question is, how much of the data is less than 0.4? So this is part of it, but we also have all of this over here to account for. All of this area needs to be added in as well. Well, this area over here is half of the entire area. So half of the area means we have 0.5 over here. So if I take 0.5 plus the 0.1554, I'm going to get an area of 0.6554, or 65.54%. Now remember, this is also going to work with the negative numbers. So when I'm asked to find how much of the data is less than negative 0.4, I look here at negative 0.4, and we're asked how much of the data is less than that. So we want this area over here. While looking at the table, the positive x values also can correspond with the negative x values, because it's symmetric and the area is going to be the same. So looking here at this area, we know between negative 0.4 and 0 that this area is going to be 0.1554. So if we know the entire area on the left side of the graph, from 0 all the way to the left, is half of the graph, that's going to be 0.5. And we know that the 0.5 is made up of the 0.1554 plus this unknown value. If we take x plus 0.1554, that's going to give me 0.5. Or I can subtract 0.5 by 0.1554. And when I do that, I'm going to have 0.3446, or 34.46%. Here's another one with a negative, and it's asking how much of the data is greater than negative 0.4. So looking at negative 0.4, we want to know how much of the area is greater than negative 0.4. That's going to be everything to the right side. Looking at the table, we see the area that corresponds with it to be 0.1554, which is the area between the x value and 0. So this area in between is going to be 0.1554. And then we need to add in all this other area over here, which is half of the graph, and that's going to be 0.5. So we add 0.1554 to 0.5, and we get 0.6554, or 65.54%. So now we've learned how to interpret the table and answer different questions based off the table. But as we said, most scenarios in life, and probably all scenarios in real life, will not have a mean of 0 and a standard deviation of 1. So what I need to do is what we call find the standardized value. The standardized value is the number of standard deviations that some number or value z is from the mean of the distribution. And what it's useful for is converting information into a normal or a standard normal distribution. So we're converting from a normal distribution into a standard normal. So for example, heights or grades or the pay of someone, we can convert into a standard normal and then use the table to analyze. So the formula we're going to use is x equals z minus m over this Greek sigma. So what this formula means is the z will be the number or the value I'm trying to convert into a standard normal. The capital M is the mean of the data, and the Greek sigma is going to be the standard deviation. Now let's look at an example of how this works. Here we have the heights of a certain group of adults being normally distributed with a mean of 68 inches and a standard deviation of 3 inches. And the question is, what percent of the group has a height greater than 71 inches? So to put this in perspective, 68 inches would be 5 foot 8, and 71 inches would be 5 foot 11. And we're trying to determine how many people have a height greater than 5 foot 11 based off the data that we've collected. So using the formula, we need to determine what do we plug in for z, m, and sigma. Well, sigma is the standard deviation. So this 3 would be your sigma. And then the mean is 68 inches. So this 68 would be the mean. And then the 71 inches would be the value that we're trying to find information about. We're trying to determine how many people have a height greater than 71 inches. So the 71 would be your z. So we plug everything in, and we get 71 minus 68 over 3, which gives me 3 over 3, which would equal 1. So we have converted the 71 into a standard normal number of 1. So now we can ask the question of, instead, how many people have a height greater than 71 inches, but now how many people have a height greater than 1, so to speak. So looking at the table and looking at the graph, we can then ask ourselves how many people or how much of the data is greater than 1. So just like we did in the previous examples, we can look at the 1 and determine how much of the area is more than 1. Well, this table, if you were to look up the number 1, the area that corresponds is 0.3413. 0.3413 is not your answer because that is the area between 1 and 0. So this is 0.3413, but we're concerned about this area. So this we can call x. And we know the area from 0 all the way on, the second half, this right half, would be 0.5. So if we add 0.3413 with x, the entire area is going to be 0.5. So what I can do is I can subtract 0.5 by 0.3413 to get 0.1587, which would equal 15.87%. So to recap, what we've done is we have converted 71 into a standard normal number, which we can then use the table to answer the question at hand. And then at the end, convert to a percent. So what we found is that 15.87% of the people that we have collected data on have a height greater than 71 inches. And that concludes our lesson for today. We will see you next time.